Continuing on with test 2, now we're on the computational problems. So, computational problem 1. A railgun can be built from a series of charged metal plates, each with a tiny hole in the center. Each cell contains a positively and negatively charged plate, separated by a distance d, and then several cells are put together in a row. When a charged particle is put at one end, the field in each cell accelerates the particle. By going through several cells, the particle can be accelerated to high speeds. Assume one cell is 10 centimeters long and has an electric field of 2.5 times 10 to the 4th newtons per meter, and assume that 100 cells are lined up to make the railgun. If a 5 microgram steel ball has an excess charge of 10 to the minus 5 coulombs, how fast will it be going when it leaves the end of the railgun? All right, so we are going to, let's try this pen. You know what we're going to do first. We're going to draw a picture, especially for this one because it sounds kind of complicated. So what we have is some cell that's like this. We know we have a excess charge of +1, so we're going to go minus to plus. So we're going to put some ball right in here. This ball is going to have a charge Q, and this ball is going to have, oops, no, I had it backwards, sorry. Plus and minus. Okay, so, yeah, so this is it. We know there's some E field that's created here. There's some E. What do we know is going to happen? We know that a Q is going to be, it's going to feel a force that's equal to QE, and in this particular situation, we know our force is going to be in the x direction. So this is going to be QE, and we know that E is constant between these 2 points. So the question is, how are we going to approach this problem? Let's see. Have I put everything? Yeah, I put. Now I will just modify this drawing a little just to include some other things. We know we have this cell, and then that's immediately followed by another cell where we have the same thing, the same identical plus and minus, and we know this is going to go all the way on for some number. We're given what that number is, but we aren't going to worry about it. And this is a mass M that's right here. So it's a Q and an M there. All right, so this is the situation we have. A charged particle, this little cell that will accelerate this charged particle with a force QE. We're going to go through a certain number, and we are asked, we start at 0, and what's the V as we exit? All right, when you see a problem like this, the first thing you should think, well, there's all sorts of different ways you can approach this problem, right? So I won't say the first thing you should say, but what I will say is this. When you see a problem like this, especially where you have a very well-defined initial kinetic energy and a very well-defined initial final kinetic energy, i.e. it will be defined once we find this V, it will be defined. And we have a situation where we can understand the change in the potential energy. Now we say this is a conservation of energy problem. So what we're going to do is we're going to try to treat this as conservation of energy. Well, what does that mean? That means we are going to get a change in kinetic energy. We're going to go from T, I'll do it this way, T final minus T initial. That will be the change in kinetic energy we got. And we know that this is going to equal minus, I'll put the minus sign out here, minus the change in, let's see, UF minus UI. Okay, so in other words, what this says is, if we gain in kinetic energy, we lose in potential energy. All right, we'll look at this, and do we know anything about the potential energy of this thing? Well, the answer is yes, we do, right? We know that let's do it this way. We know that the potential energy of a charge in an electric field is equal to the charge times the potential. So what is the potential for each of these cells? What's the potential difference that happens in one of these cells? Okay, so sorry, I'm going to make this strategy explicit. So what we're going to do is we are looking for this change in energy. The way we're going to figure that out is we're going to say, okay, well, what's the change in energy through one of these cells? And then we're just going to add up all those changes in potential energy. And once we get to those changes in potential energy all added up, we'll be done. Now, I wanted to let you know there is one little caveat to this problem that I didn't want to say explicitly because it's already written and I think you guys will be fine with this. But if we actually built this exactly the way I'm drawing here, you would be going from plus to minus here, but you'd be going from minus to plus right here in this little distance. We're ignoring that. And in fact, kind of the way that this is done in real life is you turn off and on each one of these cells one after the other. And you turn them off when you don't, when it's starting to slow you down, you turn it off. Okay, so here we are. This is what we're going to do. So now what we want to do is we want to find the change in potential energy as we go from one end of this cell to the other end of this cell. Well, what is the change in potential energy? It's just, I don't want this to turn off so I don't lose the screen. It's just QV, right? Or Q delta V, I guess I'll say. So it's Q delta V. So all we need now is to figure out what the delta V is in this little plate right here. Well, we know E is defined as minus delta V over delta X. So we know what E is, so we have E delta X is equal to minus delta V. Okay? So we now know what delta V is. So now what is the change in, that's the change in electric potential. What's the change in potential energy? Just Q times that. So Q delta V, I'm going to go ahead and put the minus sign out here, minus Q delta V is going to be our change in potential energy for one cell. So what is it for 30 cells? It's just 30 times this. What is it for 600 cells? 600 times this. So I'm just going to go ahead for the moment, I'm just going to say N. And N is just the number of cells that we have, the total number of cells that we have there. Okay, so this right here, we are now done. This is our U final minus U initial. Okay, so now we just need to worry about this other half of the equation, and I am going to erase some of this stuff here. I think you guys can remember this one, so I'm just going to erase this, even though this is not what we're doing. We're about to do that equation right there. I'm going to leave the drawing for that. We already got this. So we now know we have delta U equals, and that's U final minus U initial, is going to be equal to minus Q delta V N. And what else do we know? Well, what's our initial kinetic energy? It's 0, right? We're at rest. Our particle's just sitting there. What's our final kinetic energy? Our final kinetic energy is 1/2 mv squared, and that's it. So now we know that our change in potential energy is minus this. And if you remember the equation that I just erased, the change in kinetic energy is the negative of the change in potential energy because energy is conserved. So we know 1/2 mv, oh, I'm sorry. I'm concerned about those V's getting confused. I'm going to make up some symbol here. Let's just call it, I'll just, okay, I'm panicking. All right, I'm just going to call it eta. 1/2 eta squared is equal to Q delta V N. What are we asked to get? This eta now we're defining as our velocity or our speed, and that's what we're asked to get. So all we need to do is do a little bit of algebra, and we see that this is 2Q delta V N over, where am I? Oh, sorry, I forgot what I was doing because I forgot I erased something I shouldn't have erased. Okay, so we know that this is equal to eta squared. So I'm just going to take the square root of that to equal 8. So this is what we need. There is one more bit of information we need to remember, and that thing we need to remember is that Oh, is that we know what our delta V is, because what's our V? Our delta V is E delta X. Okay, so we have 2Q E delta X N over M, square root of that is equal to eta. So this is our answer. We are now done. Final bit, and I hope you remember to kind of do things this way. Try to do things with symbols and then put the numbers in at the very end. Final bit is just put those numbers in. I will go ahead and do that, even though it's going to add more time to this. And I tried to make this, when I wrote it up, I tried to make it end up as a nice number. I don't remember if I succeeded or not. So now I'm just going to look at this, and I'm going to say, all right, let's see what we got here. We're just going to plug in everything that we know. We know Q equals 10 to the minus 5 coulombs. E equals 2.5 times 10 to the 4th newtons per meter. You will notice I gave you the definitions for units, and what you will find, and what is easy to find, is that this is, that's not newtons per meter. I'm going to have to change that, but I will change it. Newtons per coulomb, newtons per coulomb, which is the same as this unit, newtons per coulomb, is also the same as volts per meter. And we're going to use that. I got to make a note here so I fix this before I give this test to you guys. All right. Volts per meter. Okay. N is equal to 100. Delta X is equal to 10 centimeters long, so that's 0.1 meters. Remember your units. They all have to be in meters. You know what they all need to be in. And M is equal to, where are we? 5 micrograms, which we are told is 5 times 10 to the minus 6, just in case you were not remembering. Oh. No, this is 5 milligrams. Yeah. So I got to fix that too. Okay. All right. Good thing I'm doing this before I give you guys this test. Okay. So now we just, let's see, do we have everything? Q, E, N, delta X, M. Yep, so we do. So 2Q is just 2 times 10 to the minus 5. E is 2.5 times 10 to the 4th. Delta X is just, yeah, I'll just write it as 0.1. That's fine. And N is 100. Okay, and this is over 5 times 10 to the minus 6. I'm going to ignore the square root for now. Just remember to do that at the end. So what do we have? This is 5 times 10 to the minus 1 times 10 over 5 times 10 to the minus 6. So this is just 0.5 times 10 is just 5. So I'm going to cross that out. It's just 5. So this is 1 equals 1 times 10 to the 6th. And now I'm going to pop our square root in there. And what does that equal? It equals 10 to the 3rd. So 10 to the 3rd meters per second. I am going to be looking for your units. You should at least have them in there one time. But once you can do all your units by the side once and say, yep, see, all the units work out. Okay, I'm going to leave it at that. And we are done with problem number 1.